matter of convenience that we work with logarithms. Okay. Now we're going to encounter pKa as well in a moment. All right. So we've already looked at this idea of strong acids dissociating to completion, strong bases dissociating to completion. Here we've got some examples of strong acids. Now, H2SO4 is an example of what we call a diprotic acid. Why? What does that mean? Max?
Sounds like two proton exchange, maybe?
It means that there's two protons, that the substance has two, it is an acid, and it has two protons that can behave, that are available for donation. So let's write it down. Does everyone agree with that? That is the acid dissociation step for H2SO4. So if we look from left to right, clearly this is behaving as an acid. This is behaving as a base. This is behaving, if we look from right to left, this is the acid and this is the base. So this forms an acid-base conjugate pair, and so does this. Does everyone agree with that? Okay. Now notice on the HSO4, there is still a proton sitting here, the HSO4 minus. So in fact what can happen now is a second dissociation can take place. And we end up with SO4 2 minus plus what? Plus? You guys are very docile today. Acid, base, base, acid. So it's diprotic because it has two protons that can be donated. So it's, yeah, we would talk about a Ka1 value and a Ka2 value because it's diprotic. But H2SO4 is an extremely strong acid, so it doesn't make sense to talk about Ka values for this acid because they're so high, immeasurably high, basically infinitely high. All right, we also have triprotic acids. Can someone give me an example of a triprotic acid? H3PO4, phosphoric acid, triprotic. So you can write down 3 dissociation steps. There's 3 protons available for the dissociation. Yes?
Yeah, I was going to ask another question about another thing. Is that how do you recognize the ability to be a good acid or not?
That's a very good question. Yeah. And it's difficult to say, but generally, if an acid is an organic acid, in other words, if it's bound to a carboxylic acid functionality, COOH, well, not generally, it will always be a weak acid. And generally, mineral acids like HCl, H2SO4, H3PO4 are strong acids.
But on what property, like, is it random or?
No, it's definitely not random. It's got to do with the ability of that proton to be donated. Okay? In other words, and it's got to do with electronegativity to a certain extent as well. So, how should we think about that? Well, it's a good question actually. But it's the you've got to look at the bonding situation in the acid and see how readily it would give up that acid. That's the first point. In other words, let's say the bond dissociation energy of the OH or of the H, whatever the H is bound to. First point. Second point is the strength of is the stability of the conjugate base. Because if the conjugate base is not stable, right, then the acid is not going to want to get rid of its proton, because the result is going to be a situation that's unstable. So it's the bond association energy of the acid, and it's the stability of the conjugate base. But yes, it's, one can't always readily see that, right? For example, CH3COOH, let's say in citrus, something like this, some organic acid like that, you can't really say which is going to be a stronger acid just by looking at it, right? It's sometimes difficult. Okay. Does that answer the question?
Yeah, kind of the electronegativity thing also, because HCl is like the strongest acid and Cl is kind of very electronegative.
Well, it's also the fact that Cl minus is very stable. Right. Yeah, so, yeah. Okay. Now we've looked at Ka, and here is a table showing some Ka values for a variety of acids and some Kb values for a variety of bases. Right, so let's look at, for example, iodic acid, 1.6 times 10 to the minus 1. You see here, these Ka values are quite cumbersome to write down. That's why we have the logarithmic scale, pKa, which is simply negative log Ka, and we end up with much more convenient values. So basically, the lower the pKa, right, the stronger the acid. Don't get confused. The higher the Ka, the stronger the acid. The lower the pK, because it's a logarithmic scale, the stronger the acid. And here you can see it. For example, iodic acid is a pretty strong acid. 1.6 times 10 to the minus 1, 0.16 is the Ka value. pKa is 0.8. If we get to something like, let's say, phenol, 1 times 10 to the minus 10, it's an extremely weak acid, but it's got a pKa of 10. So realize that these are sort of inverses, logarithmic scale. We have the same thing for bases. Here we've got a range of organic bases. They tend to be pretty weak bases, as reflected by these Kb values here. So for example, here we have diethylamine, ethylamine. By the way, the basicity of organic bases and acids, actually one can rationalize quite readily, but for that you need to understand organic chemistry, right? And that's where the stability of the conjugate base becomes very important. But to understand stability in terms of organic chemistry, you need to first do a course in organic chemistry. So you'll do this later on if you go on with chemistry. So pyridine, for example, here 1.5 times 10 to the minus 9. So you get the picture. So you see here, the lower the pKa, that should be overall pKa. The lower the pKa, the increase the strength. The higher the Ka, the stronger the acid. They logarithmic scale, same thing for Kb. The lower the pKb value, the stronger the base. The higher the Kb, the stronger the base. Everyone understand that? It's simple mathematics. I'm working with logarithms. I established last semester that students don't know how to work with logarithms, right? Which was very disturbing. Okay. Now, what this all boils down to is let's consider an example. So here we've got a base. This is called methylamine. And if we write the Kb expression, in other words, from left to right, we end up with this expression over here, right? So it's simply the conjugate acid multiplied by the concentration of OH minus divided by the concentration of the undissociated base, methylamine. And we can also write down, a Ka expression for this thing over here. So in other words, if we assume that this behaves in an amphiprotic fashion, in other words, in this case it's acting as a base, it can also, let's say, act as an acid, we would end up, no, I got that wrong. Yeah, sorry. The Kb expression is from left to right, the Ka is simply from right to left. In other words, we're writing now the expression of Ka from right to left. All right, and of course, that is CH3NH2 multiplied by H2O over, okay, so you get the idea. We can write a Ka and a Kb expression relating to this methylamine dissociation. Now, if you take the product of these two expressions, you end up with Kw, because everything cancels out. In fact, maybe we should do that, just to show you. It's a very important result, and it's a useful function, or it's a useful equation that we can use. All right, so Kb, for this example, this is an example, but it holds true for anything else. All right, I'm just rewriting these expressions. But that's Kb. Ka is CH3NH2 times the concentration of H3O plus divided by CH3NH3 plus. Yes. So you see basically what we've done. Yeah, okay. Now if we if we calculate Ka times Kb, what are we going to get? Let's write down the expression. Let's write down the product. Ka times Kb is going to be CH3NH2 multiplied by H3O plus, the concentration, divided by CH3NH3 plus, concentration. Remember, we're working with concentration in these expressions, multiplied by CH3NH3 plus times OH minus divided by CH3NH2. And notice everything cancels. And what we're left with, what are we left with? Exactly. Kw. We are left with OH, concentration of OH minus times H3O plus, which is nothing different than just the ion product of water Kw. And so this is a very useful expression, Ka Kb equals Kw, because it means if we, for example, given the Ka value of a substance, we can also determine its Kb value. Remember, every substance will have a Ka and a Kb value. And this sort of proves it. Okay. And that's why generally we only tabulate Ka values, because we can readily calculate the Kb value. This is a very important result. Sort of store it somewhere in the back of your mind, because if we're working with bases, for example, and I give you the Ka value, you might have to determine the Kb value, and the only way of doing that is using this expression. All right. Percentage ionization is basically another way of talking about the acid strength, okay? We can talk about the degree of ionization or the percent ionization. Basically, they're synonymous with each other. it's really another way of talking about Ka, right? Because, of course, if the percentage of ionization is higher, it means it's going to be a stronger acid. Right, I just put this here for the sake of completeness. Polyprotic acids, I mentioned this a moment ago. We looked at the example of H2SO4, H2PO4. Here we have, for example, phosphoric acid, sulfuric acid, which we've already looked at. Because they're polyprotic, right, every proton or every dissociation step is going to have its own associated Ka value. First association step might be very large, the second one might be very small. Let's have a look at an example. Sulfuric acid. The first association step affording HSO4 minus and H3O plus, Ka1, is very large. In other words, it associates to completion. The second association step, however, HSO4 minus plus H2O to form H3O plus SO42 minus, is actually not so high. It's got a pKa2 value of 1.96 or Ka2 value of 1 times 10 to the minus 2, meaning that that second association step, or the HSO4, is actually behaving as a weak acid. All right? So when you're dealing with polyprotic substances, realize that the first association step might be to completion, but the second, third, fourth, however many, one has to realize that those might not ionize so readily. And here's some other examples as well, right? So generally, the first association is always easier than the second, third, and fourth association. And you can see that here reflected in these Ka values. Notice that the Ka1 value in all cases is higher. Do you see that? 10 to the minus 7, 10 to the minus 19. Well, let's look at the pKa values. Remember, the lower the pKa, the stronger the dissociation process. So you see it's lower in each case, the first one, which kind of makes sense, right? Even from a simple statistical point of view. Okay, now, let's talk about some calculations. This is, after all, what it's all about. Being able to actually do some calculations with it. So we're going to end off this lecture, or this part of the lecture, by looking at a calculation, and then we're going to take a break. Right, here's a typical question. What is the pH of a 0.1 molar or moles per decimeter cube acetic acid solution? How do we proceed? Suggestions. I'll tell you how we proceed. Can I give a suggestion? Are you interested in my suggestion? All right, it's very simple. 0.1 molar solution acetic acid. So we want the pH. We know that pH is what? Negative log H3O plus. Well, that's easy. We've got a 0.1 molar solution. So and that's the pH. Is that correct? Is that correct?
No.
No. Why?
It's not a concentration
Yeah.
of H3O plus.
Why not?
Because that's the reactant, not the product. You need to.
It's strong.
Because it's not a strong acid. Let's play a different game. What is the pH of a 0.100 molar solution of HCl? How do we calculate that? Like that. Why? So the pH of that is simply going to be negative log 0.1, which is what? Can someone calculate that? Okay. Why is that valid?
Because we can assume that it will dissociate completely.
Correct. Because if we have HCl, it's a strong acid, it associates completely, meaning that if I've got a 0.1 molar solution of HCl, I'm going to have a 0.1 molar concentration of H3O pluses, because all of it is dissociating. However, this is a weak acid, and we can't make that assumption. In fact, the only way to deal with it is to take the Ka value into consideration, right? So let's look at how we do that. We need the Ka value of acetic acid. So let's go to the table and see if we can find it. Yes. If we look at this table, this is an experimentally determined value determined in a laboratory. There it is, 1.8 times 10 to the minus 5. So, I'm going to turn this off just so that we can have some. 1.8 times 10 to the minus 5 is the Ka value of acetic acid. Okay, does everyone understand that? What does that mean? It means that if I write down the expression for Ka, let's write the dissociation down. Okay, there it is. Now what we're ultimately trying to find, obviously, is this guy here. Because that's going to give us the pH, because the pH is negative log H3O plus. So we can't do what we did there because it's a weak acid. So we've got to take the fact that it's a weak acid into consideration. We know the Ka value. So let's write down the expression for Ka. All right. Does everyone agree that that's the expression for Ka, for acetic acid? Everyone agree? All right, so now we make an assumption. We know that we've got a 0.1 molar solution of acetic acid. Now, we've said it's a weak acid, so think about it. If I make a 0.1 molar solution of this guy here, some of it is going to dissociate in a beaker. So the concentration of this in reality is going to not be 0.1, but it's going to be very close to 0.1 because it's a very weak acid. So only a small percentage of it is going to, a very, very small percentage of it is dissociating. So the assumption we make, is that the concentration of CH3COOH is approximately equal to 0.1 molar. Even though it's going to be slightly less, because some of that stuff is dissociating. Nevertheless, that makes our life very simple, because now we can actually solve the expression for H3O+. Ka is 1.8 times 10 to the minus 5. Right, now the concentration of this and this is obviously, by virtue of the fact that we have a 1-to-1 dissociation ratio here, going to be the same. So let's call it x. It's going to be x squared over what? Over 0.1. So x is going to be the square root of 1.8 times 10 to the minus 5 multiplied by 0.1. Can someone calculate that for me, please?
So you said that we proceed in different ways depending on the strength of the acid. Right?
Yes.
So there's like, is there a line maybe that tells us if...
The line is very simple. As soon as there's a tabulated Ka value,
Okay.
right, then you've reached that line, and you have to use it. Because you either have a Ka value or you don't. If you don't have a Ka value, HCl doesn't have a value. It's like, well, it does, but it's so high
Okay.
that we don't really use it.
Okay,
Yeah.
So practically for doing an exercise, we just have to look up at the table. And
Yes. 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 And this is the way to proceed. So what's the value?
1.34 times 10 to the power of minus 3.
Is that x? 10 to the minus 3. All right, now that is, after all, then going to be the concentration of H3O plus. In what? Moles per liter. So what's the pH? So the pH is going to be negative log 1.34 times 10 to the minus 3, because, of course, this is the concentration of the H3O plus, and pH is negative log H3O plus. So can someone calculate that for me, please? Actually, it would be good if more than one person does it. Fabian and Stephanie and Alfonso and Max. Come on, guys, you're very slow this morning. I know it's Monday.
It's 2.87.
2.87 sounds correct. Can someone just validate that?
Yeah, that's right.
Okay, so notice that the value is 2.87, so you can see it's a weak acid. Alright, so that's basically how we do that. Let's reconvene in 15 minutes. I don't know about you, but I need a coffee. 15 minutes? Alright. Alright, I'll see you in 15.
I wrote that down, I have no idea. I have no idea what it is not known.